So as I mentioned in the previous video, in this last remaining two videos, we want to understand the local components of the Weil differentials in the rational function fields, particularly at the rational places, because at least we know the form of the rational places. One is p infinity, which is the pole divisor of x, and we also know that the other rational places can be determined by the constants k, constants from k. So that means these are going to denote the zero divisors of linear functions x minus a for the constants a. And in general, we understand the local components at these rational places under the framework of the proposition 1.7.4, which tells us in the rational function field 2p infinity gives us the canonical divisor, and indeed this is the divisor of the unique Weil differential, and indeed the local component of this Weil differential at p infinity makes the x inverse to -1. And we can also determine the local components of this Weil differential omega at p infinity and the other rational places pa. Of the Weil differentials omega. Here is the omega, is the Weil differential, which is described in part B. How it behaves in this particular functions. So these are the functions x minus a to the n, and we will see that when n is different from -1, this local component is going to be 0, and when n is equal to -1, this is going to be -1. And similarly, we will see that the local component of this Weil differential at rational places pa are determined in the specific for the specific functions in the function fields as when we have a function whenever n is -1, so that means this is the function 1 over x minus 1. We have this local component as 1, and otherwise we have 0. And in order to prove this proposition, particularly for part A, so by the Riemann-Roch theorem, indeed we know that if we have a canonical divisor, let me recall that if he is canonical divisor, by the Riemann-Roch theorem we know that its degree is 2g minus 2 and its dimension is g. And conversely, we can also see that if we have a divisor b whose degree is 2g minus 2 and its dimension is bigger than or equal to G, then B is also canonical. Because if we choose a canonical divisor, omega, and again, if we apply Riemann-Roch theorem, by the assumption its dimension is bigger than or equal to G, and by the Riemann-Roch theorem, we can compute its dimension as its degree plus 1 minus G plus L W minus omega minus B. And since, again, by the assumption, we suppose that this degree is 2G minus 2, we get G minus 1 L of omega minus B. And this shows us, indeed, this dimension is bigger than 1. But the degree of this divisor is 0, and this shows us by the corollary 1.4.12. The divisor omega minus B is principal, and since B is equivalent to a canonical divisor, this also shows that B is also canonical. So that means, indeed, if for this, if you consider this characterization for the canonical divisors in the rational function field, in order to prove the part A, it will be enough to check if this divisor 2 minus P infinity has degree 2G minus 2 and has dimension G. And this shows us, indeed, this is the canonical divisor. And now in part B, we want to see that there's a unique Weil differential whose divisor is 2P infinity. And in order to see that, since this is a canonical divisor, we know that this is a divisor of a Weil differential. Let me denote it by omega 1. So that means omega 1 vanishes on the other space of this divisor plus F, so particularly vanishes on the other space, but it doesn't vanish identically on this is F is going to be K of X, the other space of P infinity, because when we check the valuation of omega 1 at P infinity, this is going to be minus 2, and this is not bigger than or equal to minus 1. So this is why this is not going to vanish on this other space. And on the other hand, if we look at the dimension of the other space of 2 infinity over the other space of the divisor P infinity, by the first step of the proof of theorem 1.5.4, we know that this quotient space has dimension as degree P infinity. By the way, I made a mistake because 2 infinity is bigger than or equal to P infinity, so that means this quotient space is going to be P infinity and minus 2P infinity. Because in this case, this other space is going to be subspace of this other space. And the dimension of this quotient is determined by the degree of the first divisor minus the degree of the second divisor. This is 1. So that means these two other spaces are not identical the same. And this allows us to consider a local component of other of the function x inverse. So it means at the components at p infinity, we are going to assign the function x inverse and the other components are going to be 0. And this other lies in the other space of minus p infinity, but it is not an other of the other space of the divisor to p infinity. Because when we check Vp of E to p infinity of x inverse, when p is equal to p infinity, V infinity x inverse is going to be 1 because x inverse is the prime element of the place p infinity. This is bigger than or equal to 1, but it's not bigger than or equal to 2. So this is why this is not an other in the other space of 2 infinity minus 2p infinity. And indeed, if you look at the local component of the Weil differential p1 at p infinity of the function x inverse, so that means we can conclude that. So this is by the definition of the local component of Weil differentials. This is nothing but the Weil differential of the local other. And this is going to be not identical 0. So now we can set a Weil differential by using this constant c. So this is determined by minus c inverse times omega 1. Obviously, we can obtain its divisor as p infinity because its divisor is going to be principal divisor of this function, and the principal divisor of the constant is going to be 0. So this is the principal divisor. Omega and omega 1 are the same, and by the assumption this is going to be 2p infinity. And its local component, it's p infinity for this spatial or the spatial the function x inverse. Again, by the linearity of the local components of the Weil differential, is going to be minus t inverse omega 1 x inverse, and this is going to be minus 1 because we know that this is c. And for the uniqueness, let me suppose that omega star is another Weil differential whose divisor is minus 2p infinity and its local component at p infinity is minus 1. Then that means omega minus omega star vanishes on the other space of p infinity. So that means omega minus omega star is local component at P infinity is 0, and by proposition 178 part P. So if this difference is identical to 0, which shows that B minus B star is also identical to 0, and this shows us the uniqueness of such a Weil differential.